Hi there, everyone. This is Ms. Page. This is going to be our first lesson in Unit 1. We are going to talk about what is known as the set of complex numbers. So we're going to start with something that you've already learned about, which is the set of real numbers and its subsets of numbers, specifically the set of rational numbers and irrational numbers. So every real number fits into one of those two subsets. Every real number is either a rational number or an irrational number. And so here we're just going to kind of go through some of the most common types of numbers we should be aware of and whether they're rational or irrational in the set of real numbers. So here we're looking at our negative 9/5. So this is a fraction. Every fraction where the numerator and the denominator are integers is a rational number. And integers, remember, are the whole numbers, 0, 1, 2, 3, 4, 5, 6, and so on. And the opposites of whole numbers, -1, -2, -3, -4. So as long as your numerator and denominator are both integers, then the ratio or fraction of them is a rational number. Square root of 10. Square root of 10, some square roots will simplify and some won't. If it will simplify to like a whole number, then it would be rational. But if it cannot simplify to a whole number, then it would be irrational. Irrational, remember, means that the decimal would continue forever and would not have a repeating pattern. Square root of 10 would be like that. So this would be an irrational number. Here we have a repeating fraction. We know that the bar over the 7 means that the 7 keeps going forever. All repeating fractions can be written as fractions, similar to the negative 9/5. So that makes them all rational numbers. You may or may not know what the repeating fraction or repeating decimal rather is equal to as a fraction, but you do need to know that it can be written as a fraction, making it a rational number. Here we see a decimal, and we don't have a repeating pattern, but we do have the ellipses at the end, which means that the digits in that decimal keep going forever. And so here what we have is a decimal that goes forever but does not repeat. So previously our 5.27 where the 7 repeating, the repeating decimal was rational. But if we have a decimal that goes forever and doesn't repeat, that means we cannot write it as a fraction. It might be something like the square root of 10, but it can't be written as a fraction where the numerator and denominator are integers, so that makes this type of decimal irrational. And then we have numbers like 0. 0 is a whole number, and all whole numbers are rational. The reason is because we can always write a whole number as a fraction by giving that fraction a denominator of 1. And so that gives us a ratio of 2 integers, making it a rational number. All right, so that's what we've learned already. So now we're going to build some understanding of concept here as we go towards introducing a new type of number that is not a real number. And so here I want you to think about, well, what is the square root of 4 equal to, and why is it equal to that? So what we know is that the square root of 4 is equal to, yep, you got it, 2. So why is it equal to 2? Well, we know it's equal to 2 because 2 times 2 equals 4, where the 4 is what we call the radicand of the square root. Here then is another question. So using the same logic as we used to explain why the square root of 4 is equal to 2, what is the square root of -4? So here you might be running into a bit of a problem because here 2 times 2, it's a number times itself that gave us that 4. That's the definition of a square root. Here we're looking at the square root of -4. And we have an issue because, well, -2 times 2 is equal to -4. And those are not the same, so it doesn't fit that definition. So here is why we have to introduce a new type of number. So the set of real numbers, which is rational numbers and irrational numbers, both positive and negative, doesn't allow us to find an answer to this problem of what the square root of -4 is equal to. So instead, we have to use a larger set of numbers that we call the complex numbers. And specifically, we have to use what we refer to as the imaginary unit, I. The imaginary unit I is by definition now equal to the square root of -1, which we can't simplify that. So it is represented by the symbol I. So anytime we're dealing with a square root of -1 factor, we use I to represent that factor. So now we can actually simplify and figure out what the square root of -4 is equal to. So you might recall from prior learning that we can rewrite square roots as products of two other square roots. So here we're looking at the square root of 4 times the square root of -1. And in that case, what we have here is the square root of 4 we can simplify to the whole number of 2, and the square root of -1 now is what we call our imaginary unit that is equivalent to the symbol we use for it, which is I. And that makes the square root of -4 now equal to 2i. That also then means that 2i times 2i must be equal to -4. So how is that possible? Well, when we multiply these together, we have 2 times 2, which is 4. Then we have I times I, and anything times itself is squared. So that's I squared. When we're looking at something like I squared now, what we're looking at is understanding, well, that's the square root of, the I is the square root of -1, and we are squaring that. And so the square and the square root will cancel each other out. That leaves us with -1, and 4 times -1 then is our radicand of -4. All right, so that's the big idea here, is what is I, and how does it help us find or simplify the square roots of negative numbers? So now we're going to look at some more formal mathematical terminology or vocabulary. So we've talked in informal terms about complex numbers, but there's a formal mathematical definition of complex numbers that say that they are numbers that can be written in this form, a plus bi. Now the a in this form is what we call the real part. And the b, the a, although the a and the b are both real numbers, the a is called the real part, but notice the b is attached to the I. And the I is the imaginary unit, so we call that bi part, or the b part, our imaginary part. And these are some examples of complex numbers that are in this full form with non-zero values. So we have -3 plus 4i, 7 minus I. So in each of these, the real parts would be the -3 and the 7, and the imaginary parts would be the positive 4i and the -1i. The imaginary unit we've already defined. Imaginary unit, when we use that terminology, that's our I, and we have to know that I is equal to the square root of -1, which we can't simplify any further, that's why we use I. Pure imaginary number. Well, a pure imaginary number comes from square roots of negative real numbers, like that square root of -4. That was an example of a pure imaginary number. And when they're simplified, they end up with an I in them. So like 8i and -2i. Those are both examples of pure imaginary numbers. And then also part of the set of complex numbers are the real numbers, which you've already learned about. The real numbers are a subset of the set of complex numbers. And so real numbers, remember, can be rational or irrational. And in this case, the imaginary part of them is equal to 0. So it's like, we know we have 5 and -3, they're rational numbers. Well, 5 could be written as 5 plus 0i, because anything times 0 is 0, so that's just 5. -3 can be written as -3 plus 0i, which would just be -3. And then an irrational number like the square root of 7, that could be written as the square root of 7 plus 0i. which again, that's just like adding 0, so that's the same thing as the square root of 7. So 3 types of complex numbers. Summing it all up here, we have our full complex numbers that have an a and a bi part that are not 0. Then we have our pure imaginary numbers, which have an a part of 0. So this is like 0 minus 5i. And then we have our real numbers, which have an I part of 0. This is like 3 plus 0i. All right. Here's another way of looking at the set of complex numbers as a Venn diagram. So we have our overall large set of complex numbers, which all fit into the format of a plus bi, and that would include numbers of this type. But then we have our 2 main subsets of numbers. We have our real numbers, which end up just being the a part. So we can be rational or we can be irrational in that case. Then we also have our pure imaginary numbers, and that is where the a part is 0. So we end up with just a bi part. And we can have like an integer times I, we can have a decimal times I, we can have an irrational number like the square root of 7 times I. The big thing is that it's a real number times I. That's a pure imaginary number. All right, so here, one of the skills that we're going to develop is being able to simplify the square roots of negative real numbers. We should realize that each of these represents a pure imaginary number, a number times I. All right, so using properties of square roots, we can take something like our square root of negative 49, and we can rewrite it as a product of 2 square roots. So one of them we'd want to use would be the square root of 49, because that is a positive real number. And then we'd have times the square root of negative 1, because 49 times negative 1 equals our negative 49. And then we would simplify each of these parts separately. So we know the square root of 49 is 7 times. We know the square root of negative 1 now is by definition our imaginary unit I. And so that means that the square root of negative 49 would be equal to 7i. Similarly here with the square root of negative 25, then we'd look at this as the square root of 25 times the square root of negative 1. Square root of 25 is 5. Square root of negative 1 is I, which gives us an answer of 5i. The third one here is a little bit different. We have the square root of negative 32. So we would still look at it as the square root of 32 times the square root of negative 1, but 32 is not a perfect square. So part of your prior knowledge is how to simplify or rewrite these square roots. So remember that we're looking for rewriting the square root of 32 as a product of 2 or more square roots, where at least one of the numbers is a perfect square and a factor of our 32. Now, what I want you to think about for a moment is, well, what is, say, the largest perfect square factor of 32? You might have said 4, which 4 is a perfect square factor of 32. It's 4 times 8, but it's not the largest perfect square factor. And the largest perfect square factor is 16, because if you look at 4 times 8, well, 8 is 4 times 4. So you really have a 4 times 4, which is a 16, and that's the largest perfect square factor. So it's always best to kind of go that extra step and think about, okay, is this perfect square factor the largest, or is there one bigger? Because that'll save you some time in simplifying completely. So we look at this, the square root of 16 times the square root of 2, and then we still have our square root of negative 1. So we have our square root of 16, which then now is 4, times our square root of 2, and then our square root of negative 1 again is our imaginary unit of I. Make sure that you put this into that BI form, which means that you put the I at the end, but make sure that it doesn't look like the I is underneath the square root. It's times the I. That's separate. All right. So now we've got a couple of practice problems. I encourage you to pause the video here, try each of these problems, and then come back when you're ready to check your answers. All right, let's take a look at the answers. So the square root of negative 81, you should have come up with 9i. And then the square root of negative 20, 20 is not a perfect square factor, or a perfect square, but it does have a perfect square factor of 4, which becomes 2. The square root of 5 times stays the square root of 5, so you end up with 2 root 5i. All right, another type of skill we're going to develop is being able to take a set of numbers and correctly classify each of them to their best possible place in a Venn diagram within the set of complex numbers. So some numbers are complex numbers, but they don't belong in either of the two main subsets, such as real numbers or pure imaginary numbers. And within the set of real numbers, we also have two main subsets of rational numbers and irrational numbers. So if we have a real number, we have to figure out which of its subsets it belongs in. All right, so let's take a look at our first number here, negative 8.4. Negative 8.4 is what we call a terminating decimal. All terminating decimals can be written as fractions, which makes them rational. Square root of 50. Square root of 50, when you look at square roots, you want to think about how they'll simplify. And when they simplify, will they have an I? Will they still have a square root? What's it going to look like in its final form? So the square root of 50 is, since 50 is positive, this is not a pure imaginary number. And since 50 is not a perfect square, this would actually then make it a irrational number. It would simplify to 5 root 2. Because 50 is 25 times 2, and the square root of 25 is 5. Next number we're looking at is 1 minus the square root of 5i. Notice its structure. It has subtraction, and it has two parts. 1 is a real number, and root 5i is imaginary. So it has a real part and an imaginary part, which makes it a complex number, but not part of either of the subsets. So it's 1 minus root 5i would go here. Negative 3i. Because its real part is 0, this would be like 0 minus 3i, that makes it pure imaginary. That's a BI form of a number. 7/3. All fractions, when the numerator and denominator are integers, like 7 and 3, is rational. 2.83 repeating. We talked about this earlier. All repeating decimals can be written as fractions. Even if you don't know how, you need to know that you can. It is possible. And so that makes it rational. Negative 2 plus 3i. We're again looking at that a plus bi form where a and b are not 0. That makes it complex, but not part of the subsets of real or pure imaginary. So it belongs here. And then our square root of negative 16. We have to realize that in simplified form, because it's the square root of a negative number, it's going to involve I. This would be the square root of 16 times the square root of negative 1, which is 4i. And so the square root of negative 16 would go here. Notice that in the Venn diagram, I'm putting the original form of the number, not any simplified form. So for square root of 50, I used square root of 50, not 5 root 2. For the square root of negative 16, I used square root of negative 16, not the 4i that it's equal to. That's what you should be doing. Keep the numbers in their original format. All right, so let's close up this lesson here. So let's see how well you can do with identifying or finding examples of certain types of complex numbers. So the first thing I would like you to do is see if you can come up with a pure imaginary number. All right, here are some sample answers. 2i, negative 6i, or the square root of negative 5, which of course would simplify to the square root of 5 times I. So the key thing is there's no addition or subtraction, and it's a number times I, or it can be written in simplified form as a number times I. All right, how about a real number that is also a rational number? So basically, another way of looking at that would be a rational number, a real number that is also rational. All right, here's some sample answers. Integers like negative 5, regular old fractions like 2/3. You might have done a terminating decimal like 7.1, or a repeating decimal like 10.2 repeating, or square roots of perfect squares, because that would equal to the whole number of 5. You may have also even done a mixed number, like 1.5. That is also rational because you can rewrite it in its improper fraction form. All right, how about now a complex number that is not a real number? So it has to be a complex number, which all numbers that we're working with and been talking about today are complex numbers, but it cannot be a real number. All right, let's see some samples. So here you might have done an a plus bi number like -5 plus I or 2 minus 3i. You might have done a pure imaginary number like 5i or the square root of -4, which is 2i. And so those are your two options. Those would all be complex numbers that are not real numbers. If you did something like the square root of 2, nope, sorry, that's irrational. Remember, irrational numbers are real numbers. And rational numbers, like all of these, are also real numbers, so you couldn't have done any of those. All right, now how about a complex number that is not pure imaginary? Try that one. Let's take a look at some samples. So, complex numbers but not pure imaginary. You could choose anything that is real, rational or irrational, or you could choose an a plus bi form complex number, like -5 plus I or 2 minus 3i. All of these are real numbers. The 5 and the 5/2 and the 9.6 repeating are all rational numbers, and the square root of 7 is an example of an irrational number. All right, that finishes up this lesson. I hope you have a wonderful day.